Hello everyone. This is our fifth interactive session on circular dichroism and Mossbauer spectroscopy. In the last few lectures, few interactive sessions, we have discussed how to find out point group and symmetry elements of a particular molecule. Then we looked into how we can find out the chirality in a molecule, and then also why chirality is important in our daily life and biological systems, etc. And in the last lecture, also, we were discussing some of the examples how we can find out the enantiomeric excess, like how a particular light will be rotating a chiral molecule, like how chiral molecules will be rotating the plane polarized light into, like, in the like it is levorotatory or dextrorotatory. These kind of topics we have discussed already. So now we are moving a bit into how circular dichroism evolves, generates out of these concepts, and we will be revising the concepts being taught in the main lectures today. So there are not much questions we will be solving, but instead we will be discussing some of the concepts which have been already discussed in the main lectures by Professor Arnab Datta. And hopefully we can I'll try to solve a few examples of some molecules, and we will find out the point groups in those molecules, and then we will relate which of the molecules are there where which are active for circular dichroism. So uh, first of all, we will summarize whatever which have been taught in the last lecture. So I'll take 2 more minutes. I'll wait for 2 more minutes, and we will start at 6:05 p.m. And we will discuss whatever we have planned. Okay, so let's get started now. So, for example, we have a right hand circularly polarized light, RCPs, right hand circularly polarized light. And then we also have a left hand circularly polarized light. Okay, so if these two circularly polarized lights, that is RCP and LCP, are passed through a chiral sample, we have already studied that this chiral molecule, if a molecule is chiral, then it will rotate this plane polarized light in a particular direction at a particular angle. So which we also call optical rotation. So what is expected out of it? So this chiral molecule, this chiral sample, rotates this right circularly polarized light in right direction, such that we get uh, we get the resultant uh, plane polarized lights in all these directions. But also this chiral sample not only rotates this plane polarized light, but it also absorbs this light, and hence and a decrease in the intensity of the resultant light will be observed. So let's say this chiral sample is not only rotating this left hand circularly polarized light, but also absorbing this light. So the resultants are optically rotated polarized lights, but also with a decrease in the absorbance. So here we can say that absorbance of the left hand circularly polarized light is not equal to absorbance of the right hand circularly polarized light. So as a resultant here, if we see, the light we will get is like this. So the resultant polarized light we get out of this chiral sample is not only optically rotated, but we also observe a decrease in its absorbance. So the resultant plane polarized light is this. So in this resultant plane polarized light will overall be represented as, and this is not in a circularly polarized light, but the resultant is an ellipse. elliptical motion. So the resultant resultant polarized light is not in plane, but in elliptical form. So the point here is that right hand and left hand light, plane polarized light, plane polarized light can be absorbed in different ratios. Absorbed in different ratios along with optical rotation of the light. Of the light by the chiral sample. So this elliptical pattern of the resultant polarized light we have got here is such that this is the major axis and this is the minor axis. And the angle between the absorbance of the left hand rotated light and right hand rotated light is said to be psi, and the angle, this tangent, this is represented as tan psi equal to minor axis by major axis, which is equal to absorbance in the absorbance of the left circularly polarized light minus absorbance of the right circularly polarized light by the summation of both these two, of the absorbance of these two lights. Okay. So case in the condition when this angle psi approaches to 0, such that tangent psi will result out to be psi, and when we calculate it the values comes out to be al minus ar 180 degree by 4 pi degree. This psi angle for an ellipticity is proportional to the difference of absorbance of left hand circularly polarized light and right hand circularly polarized light. That is, psi is proportional to the change in the absorbance. So, for example, the formula for absorbance according to Beer Lambert's law is A equal to epsilon LC, where epsilon is molar extinction coefficient, L is the path length, and C is the concentration of the sample. So, if the resultant absorbance for the left hand circularly polarized light is epsilon L CL, because concentration for a sample concentration and path length in the sample holder will be same, and therefore these are the resultant absorbance we get. So this psi angle is proportional to the difference of this resultant absorbance in both directions. So psi will come out to be also proportional to the difference in the molar extinction coefficients. That is, psi is proportional to the difference in molar extinction coefficients of lights absorbed in different uh, directions here, that is left hand and right hand. And this difference is said to be molar ellipticity, this is what we call ellipticity effect. And this ellipticity effect give rise to the phenomenon of circular dichroism. So if we have a plane polarized light, such that right hand and left hand polarized light are differently absorbed by the sample, that is with different magnitudes. Then it give rise to phenomenon of circular dichroism. So circular dichroism is just the absorbance is related to the absorption of two different lights, and the effect is ellipticity. So the right hand component and left hand component of a plane polarized light are differently absorbed by the sample, so it gives rise to two differently absorbed color lights, and this phenomenon is called circular dichroism. So this right hand circularly polarized light and left hand circularly polarized light are when passed through a sample, we get a resultant optically rotated light in different directions, and the angle at which this light is rotated is called phi, and this and the effect is called optical rotation, that is rotation of light at a certain angle, which is uh, which is this angle phi. And the reason behind this optical rotation is circular by bifringence. So here two phenomena are taking place together. One is the effect of optical rotation, and the other effect is ellipticity effect. That is, optical rotation phenomena is related to the speed of light with which a particular right hand circularly polarized light or a left hand circularly polarized light uh, interacts is rotated by the chiral molecule in the sample. And this ellipticity effect is a resultant of the absorbance of this light. So one is how fast one of the polarized light is interacting with the sample, and other is the absorption of this light which is falling on this sample. This phenomena with the right hand circularly polarized light, and out of this right hand circularly polarized light and left hand circularly polarized light, if this LCP is absorbed by the sample, giving us a difference in their absorbance, is called circular dichroism. And the effect we get is ellipticity. This is what we call ellipticity effect. So both circular dichroism and circular birefringence can take place together, such that I'm showing how these two phenomenons together give rise to the resultant light we get out of the chiral sample. So here we can see that light has been optically, this light has been rotated at a certain angle which is phi by the chiral sample, and also it has been observed that the left hand circularly polarized light has been absorbed by the sample, giving us as this psi angle, which shows the differential absorbance of the two polarized lights. So this is two phenomenons taking place together. So the next is physical origin of optical activity. So if we have a molecule in its ground state and we incident electromagnetic radiation of a certain frequency, then the electrons in the ground state will be excited to the this excited state, and this h nu is the operator, the change we are bringing into the uh, in the state of this electron, that is it was in ground state. And what was the operation that leads to its excitation? So whether a particular transition is allowed or not, that is defined by transition moment integral, which is psi star excited state operator O psi ground state d tau. So this operator is the change in dipole moment. That is, this is dipole moment operator. So this is nothing but how we are changing the electron distribution in a molecule. So this dipole moment operator can be of three different types. That is, first is electrical dipole moment, which is the dominating factor. Electrical dipole moment mu e, so which is like always there in a molecule. So for example, even if the shape of a molecule is non-uniform, so we can say that certain electron density in a molecule is distributed more on one side than the other. So there are this electrical dipole moment is the always dominating factor in a molecule and is considered to be the main factor for a particular transition. That is distribution of electron density. And then this is as a resultant of electric field. And the second is magnetic dipole moment. The magnetic dipole moment is generally not dominant because the magnetic field is weak, and it doesn't produce much effect on the distribution of electrons in a molecule, or we can say the charge separation in a molecule. And third is the electrical quadrupole moment. This quadrupole is also very weak, even weaker than the magnetic dipole moment, such that its value comes out to be negligible. Be negligible, and therefore it is neglected in the transition moment integral. So the two main dipole moment operators, which defines whether a particular transition will take place or not, is dependent on the electrical dipole moment and the magnetic dipole moment. So this electrical dipole moment factor is dependent on the distance vector. E charge of the particle and r is the distance vector that depends on the xyz Cartesian coordinates towards which the electronic distribution due to this electric dipole moment uh, is present. So this shows that electrical dipole moment interacts along a line so that it is associated with the wave along a, let's say this is the x co- x cord x axis, x coordinate axis, and we have incidental light. The resultant light will be an increase in the amplitude of this electron wave, which we call that its oscillatory strength has increased. Now the question is how dipole this magnetic dipole moment interacts. So how this magnetic dipole interacts? It is generally perpendicular to the this magnetic field is generally perpendicular to the electric field. So this magnetic moment vector is directly proportional to the cross product of distance vector, that is xyz coordinates, into momentum of the particles, and that is momentum vector. So magnetic moment interacts along x, y, and g axis along with momentum vector. So this magnetic moment moves in a circular way. So if this is electric field, electric dipole moment, then magnetic dipole moment is associated perpendicular to it and moving in a circular way. And this is defined by rz, that is rotational z axis, or rotational xyg axis, we can say. So mu m is basically associated with rotational x rotation vector along x axis, y axis, and g axis. So if absorbance For the absorbance of light, this absorbance of light is mainly is dependent on this intrinsic molecular property, the molecule, which we call molecular extinction coefficient, which defines the oscillatory motion or strength of the oscillatory strength or oscillatory motion of the molecule. So, in the case of electric dipole moment only, we look into the absorbance of this light, which is associated with the oscillatory strength of the molecule. But in the cases where we have both electric dipole moment and magnetic dipole moment, where this magnetic dipole moment is dependent on the rotational strength, is defined by the rotational strength of the molecule. When both of these are active, then it is defined by rotatory strength of the molecule. So when we have this electrical dipole moment and magnetic dipole moment, so electrical dipole moment interacts along the line, and magnetic dipole moment interacts in a circular way perpendicular to the electric dipole moment. So when in the systems where both are active, the kind of motion we will get is helical motion. And both of these are mirror images of each other, like this helical motion we get from the right hand and left hand circularly polarized light. uh, so if we have A right hand circularly polarized light moving in an helical motion, and left hand circularly polarized light, which is a mirror image of this right hand circularly polarized light but non superimposable, are passed through a chiral sample which can detect this helical motion. So we have to take such kind of chiral molecule which can detect helical motion such that it can excite both electrical and magnetic dipole moment. Such kind of molecules are said to be optically active and CD circular dichroism spectroscopy active. So for a molecule to excite both electric dipole moment and magnetic dipole moment, its distance vector, that is xyg vector, and r, this its rotational vectors along the respective axis should be associated together. So this kind of transition will be allowed when both dipole moments are active in this, and we will get either 0 or 1. If we are getting 0, then that transition will be forbidden, and 1 is for allowed. So the cases where it is allowed, this transition is allowed, are the molecules where both the distance and rotational vectors are associated with each other. So only if we are getting a totally symmetric representation, then that transition will be allowed. So in a character table, so firstly we have to find out in a molecule we have to find out symmetry elements. Based on those symmetry elements, what is the point group of the molecule? And then we have to check the character table. So for each point group there are character tables, uh, that is mathematical tables, we can say, where all the symmetry elements associated with a particular point group are collectively represented based on certain mathematical or certain rules. So we won't go that deep. So you can look for the character tables of each point group. So in that character table we have, here we have symmetry elements in one column, all the symmetry elements which are classified based on certain rules. Here we write the n- name of the point group. Here we have irreducible representations in the first column, and the number of irreducible representations are equal to number of classes in which all the symmetry elements are represented. And in the second column, for each symmetry element, we have representations, irreducible representations, and in the here we get the name, and here the values with associated with each symmetry element. In the third column, we have linear functions for each irreducible representation, and in the fourth column, quadratic functions are represented. So this linear functions, this third column is where we have to look whether we have x rx, y ry, z rz, that is distance vector. These distance vectors x y g are represented along with the rx ry and rg. So there can be cases where we have x associated with rg, or we can just have rg in that for that particular irreducible representation, or only x. So the only cases where we will get, so the only cases where each distance vector is associated with the rotational vector along the same axis is where we have to look for, and only those molecules will be said to be circular CD active. That is the only molecules we can say where electric dipole moment and magnetic dipole moment both are active. So what are the groups? So the cyclic CN group and dihedral group DN are the only groups meeting the condition where mm, electric dipole moment and magnetic dipole moment both are active. So now we will look into a few examples. So where we will find out whether these two criterias are being met, that is electrical dipole and magnetic moment are both active together in the same molecule. And for that we have to take certain examples. For example, if I take this BH3 molecule, so firstly we will find out the symmetry elements for this molecule. So we know, so now till now we have already discussed how to find out symmetry elements in a group and how we can trace to which point group a particular molecule belongs to. So that flowchart we have already discussed. I'm not going into much details here. So I will directly find out that this molecule BH3 molecule has C3 axis of rotation. Then it has 3 C2 axis of rotation perpendicular to the principal C3 axis of rotation, which are passing through each of the BH bonds. And it also has a horizontal plane perpendicular to the principal axis. And there are also three vertical planes passing through each of the BH bond, which contains the principal axis on it. So like this we have 3 sigma v's. So here in this molecule we have identity operation, then C3 axis of rotation as the principal axis, 3 C2, then sigma h, and 3 sigma v. So the point group this BH3 molecule belongs to is of BH3 is D3H. So if we now draw the character table for this D3H point group, table of D3H point group is, so in the first column we represent the names, we write the names of each irreducible representation. For more details about how we can generate these character tables, you can look into the symmetry and point group uh, course. So I'm writing it directly here. E2C3, and here in we write the name of all symmetry elements and classify into different classes based on certain rules. So in the fourth column is where we write the linear functions. So with respect to A2 dash irreducible representation, we have RZ linear function, and with respect to E dash, we have X and Y coordinates. And then Z is associated with A2 double prime irreducible representation, and Rx, Ry are associated with E double prime irreducible representation. So here we can see there is not there is no irreducible representation where both where this where we have both the distance vector and rotational vector associated together along the same coordinate axis. That is, there is no irreducible representation where this condition is being satisfied. This condition is not satisfied, which means both electric dipole moment and magnetic dipole moment are not active together. So if we take another example, let's say of if we take this delta trans cobalt ethylene diamine twice Cl2 positive molecule. So if we represent this molecule, And if we find out the symmetry elements in this is in this molecule, we can see that we have a C2 axis of rotation passing through the Cl-CoCl bond, and also we have a C2 axis perpendicular to it. Other than this, this is C2G, this is C2Y, and then we have C2 axis. So in this molecule, the only symmetry elements present are identity operation and C2X, C2Y, and C2G axis, that is C2 axis of rotation along X, Y, and G coordinates. So the point group of this molecule is molecule is D2. So if we draw the character table for this D2 point group, X, so here the linear functions will be represented, and in the last column again quadratic functions will be. So here we have equal to the number of classes. We have four classes, so we have four irreducible representations, which are A, B1, B2, and B3. So if we write the linear function corresponding to each irreducible representation, we will see that with G, with this B1, we have G and RG functions associated. Similarly, for B2, we have Y and RY, and for B3, we have X and RX. So, as we have already discussed, that in the case of Cn and Dn point groups, both the conditions will be satisfied will be satisfied such that we have distance coordinates x, y, g uh, are associated together with their rotational vectors r, g, r, y, r, x, etc. So here both mu m and mu e will be active. So this is how you can find out what kind of sample we are taking, and how we can directly look for the whether this sample has electric dipole moment and magnetic dipole moment are active or not. So these are the two examples which I have shown. You can also look for Cn and other examples for Cn and Dn. So this is where all our previous lectures concepts will be applied, where we found out the different symmetry elements and then the point groups for each of the molecule. So those if you have practiced those examples, it will be helpful for you uh, to find out to apply those concepts here in this concept. So we can say molecules belonging to Cn and Dn point group can detect helical motion of light as in such molecules both electric dipole moment and magnetic dipole moment will be active. So for a molecule, if if we record the absorption spectra, then for the sample we will get a single peak in the absorption spectra, because The optical rotation phenomena, which gives rise to circular birefringence. This optical phenomena comes out of the difference in the speed of light at which uh, at which it depends on the different speeds of light at which both of the right hand and left hand circularly polarized lights interacts with the molecule. But if we record for the same sample a spectra of optical rotation versus the wavelength of incident light, then we will see the same sample for two different enantiomers of that molecule, of the chiral molecule. We will get two different spectras in this, two different curves in the same spectra. One, for example, this is for enantiomer 2. One is for enantiomer 1. So for two different enantiomers, we will get two curves in the same spectra. Where one is moving from positive optical rotation to the negative optical rotation, and the other is moving from negative optical rotation to the positive optical rotation. So this where the spectra where the optical rotation is increasing, it is called positive Cotten effect, and where the optical rotation is decreasing, it is called negative Cotten effect. And this spectra is a resultant of the speed with which two different lights are interacting with the chiral sample. So here we can have reasons where absorbance will be equal to 0, but optical rotation is not equal to 0. So if you see in this absorption spectra corresponding to the wavelength which has the maximum absorbance, we in the optical rotation spectra we are getting a 0 optical rotation at this point for both the enantiomers. Why? Because in at this wavelength the light has been completely absorbed, so there is no concept of its optical rotation when it's come out of the sample. So basically we can say here the absorption is maximum but optical rotation is 0. But in other reasons we can say we have certain amount of optical rotation along with its absorption in a particular wavelength region. So this was the case for the optical rotation versus wavelength spectra. So now what about the ellipticity effect, where the two incident lights, that is right hand circularly polarized light and left hand circularly polarized lights, are differently absorbed by the sample. So what kind of spectra we will get in that case? So if we discuss about the ellipticity effect, so this is called optical rotatory dispersion spectra. Optical rotatory dispersion spectra, that is the difference in optical rotation of two different polarized lights by a chiral molecule gives rise to this optical rotatory dispersion spectra. But due to the ellipticity effect we get a circular dichroism spectra, and we will see how it is represented. So again, if we record the absorption spectra of a molecule, and we record a psi versus wavelength spectra, that is difference in the absorption of two polarized lights by the chiral molecule. Sorry, I think from last few minutes my screen is not being shared. I don't know what was the problem here. Let me repeat it. So in this case, for two different enantiomers, we will get two spectra. That is, this is for enantiomer 1, which gives positive psi values, and the another is enantiomer 2, which gives negative psi values. So this is what we call positive Cotten effect, and this is negative Cotten effect. Since psi is equal to Al minus Ar, that is, it is proportional to Al minus Ar, if the left hand light is absorbed more by the chiral molecule, then we will get this positive Cotten effect, and the enantiomer which is absorbing this right hand circularly polarized more, we will get a s- negative psi value, and that is what we call negative Cotten effect. So if we have an absorption spectra, and we record a CD spectra corresponding to it, there in the region where we are finding the curves in the CD spectra, that region we can set that that particular region is optically active. So we have almost covered the topics of the last lecture, and not much content is left to discuss for like 20 minutes. I'll try to take a few examples. So if we take an example of CN point group, let's say we have S2O2. So it has an open book, or we can say open laptop geometry. And if we have to find out the symmetry elements in this group, so we can see that it has a C2 axis of symmetry, it has identity operation, and C2 rotational axis present in the molecule. So the symmetry elements present in this molecule are E and C2. So the corresponding point group is C2 point group. And the character table for C2 point group is, so here we have two irreducible representation corresponding to classes that we have E and C2, and the linear functions are, here we have ZRG associated with a reducible representation, and the XY and corresponding RX and RY rotational axis functions also associated with the same irreducible representation. So we can say that this C2 point group molecule S2O2 can detect helical motion as it has both mu e and electrical dipole moment and magnetic dipole moment active. So if we summarize today's lecture, we can say that circular dichroism is an absorption spectroscopy method based on the differential absorption of left and right circularly polarized light. So the optically active chiral molecules, that is molecules which belongs to C and Indian point group, optically active chiral molecules will preferentially absorb one direction of the circularly polarized light. So for a particular wavelength, a circular dichroism signal can be positive or negative, depending on whether left circularly polarized light is absorbed more than right circularly polarized light, or less, like we can say more or. So I think this is it for today. So if you have any doubts and you are following the lectures, please try to attend these interactive sessions, because one way these sessions are not much helpful for me and you also. Uh, when these are interactive sessions, so we are more involved and we get to discuss the required content, instead of just taking the different examples or revising the content. So please try to join these sessions. Okay. So thank you so much for today. See you in the. So we will meet in the next session. I hope you guys will join and you are following the lectures on YouTube. These recorded sessions you can also find the links on the main of the course website, like this NPTEL site. And also, if you have any doubts, you can share it in the discussion forum. And thank you for your attention.